So hi, I'm Hunter from Way Robotics team. This is Kenny, and yeah, this is our presentation. Uh, as you can see in the background, this 3D model that we've been working on that kind of shows the final product of our robot. Yeah, go ahead. Thank you. All right, so yeah, first of all, we have game rules. Keep going. Okay, so game rules before the match. All robots must be in compliance with the robot rules and pass inspection before entering a match. So typical inspection done, and you have to follow every single guideline in that area. The robot must be in a starting configuration and must be constrained to a volume of 33 inches by 28 inches by 55 inches tall, with the exception of the bumpers. So starting configuration meaning when the robot is lined up against the wall, it has to fit into that volume. And then as soon as the match begins, you can fold out or do whatever you need to do when you're climbing, whatever. The robot may not support more than one power cube during and before the match. So it can only have control over one power cube. It says also in the rules more specifically about how control is defined as far as pushing the cube and all those other definitions. So yeah. Game rules, auto/teleop. Power cubes may not be removed from the vault. So when a human player puts a power cube into the vault, get your points, you cannot remove it or move it to somewhere else in the vault. Once it's there, it's there. Teams may not interfere with any automated scoring hardware. So you can't, directly, mess up any of the game field components or attempt to disable them or anything like that. Teams may not modify power cubes in any way. So that means destruction or, adding onto them, modifying them, etc. You cannot tear them. You have to be very gentle. Robots may not intentionally detach or leave parts in the field. So everything's got to be secure before the match, and hopefully after inspection that all got cleared up. But if you lose a bumper, lose any part of your robot, can receive fouls. Robots must be in compliance with bumper rules throughout the match. So fitting the perimeters with the bumpers, again, can't leave your bumpers on the ground. They have to be tight and fitted and not loose. And again, no interfering with other robots. Things like that has to be safe. A robot is not permitted to launch power cubes except when any part of its bumpers are inside its alliance's null territory and it's attempting to place a power cube on the scale plate in its alliance's null territory. So to summarize that real quick, basically you're not throwing power cubes, you're not throwing them at other robots or anything unless you are directly trying to score points on the switch of the scale. And again, B, when any part of its bumpers are contacting a fence and it's attempting to place a power cube on the nearest plate of that fence's switch. It just said C, when any part of its bumpers are inside its alliance's exchange zone and it's attempting to place a power cube in its alliance's exchange tunnel. So when you're either trying to put a cube on the switch, the scale, or delivering to that exchange zone. Game rules, robot-to-robot interaction. Strategies aimed at the destruction or inhibition of the robots via attachment, damage, tipping, or entanglements are not allowed. That's pretty self-explanatory. Again, no destruction. You cannot physically attempt to disable a robot or harm it in any way. Initiating deliberate or damaging contact with an opponent robot on or inside the vertical extension of its frame perimeter, including transitively through a power cube, is not allowed. So again, relatively the same thing. You cannot use the field component. Do you have a question?
No, he's doing the timing.
Oh, okay. I can't see that far. I'm sorry.
I think time.
Oh, I'm done?
Yeah.
Oh, all right. Sorry.
All right, yeah, I guess I should have said that a little more explicitly. So Keith has some cards back there, and they'll hold up yellow when you're getting close to the end, and and red.
I see. Okay, sorry about that. So switching.
Switching. Yep.
All right, got it. Sorry about that.
Tag, you're it. Okay, so now let's hear about the rules relating to robot construction. What can you do and what can you not do?
Hi, my name is Olivia Loney.
My name is Ely.
My name is Nisla.
So these are the robot roles. So this year we're constrained to a volume of 33 inches by 28 inches by 55 inches tall, and our bumpers must be 6 inches and cover the entire perimeter. We cannot reach 16 inches beyond this perimeter, except during the end game when we're climbing. And also our weight cannot exceed 120 pounds, and this is not including the battery or the bumpers.
So this year, this is about actuators. So this year we can use an unlimited amount of specified types of motors. So behind me there's a chart, just like some of the motors that we can use. The only restrictions to that are the amount of connections on our power distribution panel and your battery. So on our robot, we're actuating our intake, and the wheels on the intake.
So for our power sources, we have our batteries, and if you don't have your battery, you can't move or power. And it's a 12-volt battery, and it's rectangular, and it should look like that, or and it should be placed on your robot so that even if you flip over, it stays on. And so we made a battery box and secure.
That it? Okay.
Any questions?
Okay, so
Okay, round two. All right, so here's our strategy and design. Go ahead, Kenny. All right, strategy. Our team's main focus for this year's game is the switch. By controlling both alliances' switches to be in our favor, we can earn the same amount of points as an alliance that controls only the scale. Assuming we have control of the other alliance's switch, using power-ups to boost the points we earn from our switch only requires 1 cube to activate it and could earn twice the points of a scale-focused alliance. The scale requires 2 power cubes to boost its points. So our total height here is 36.5 inches. Our total robot width is 27.5 inches, and our total length is 32.25. Manipulator 1, the cube chute. Due to our choice to become a switch-focused robot, the chute mechanism is a simple but efficient design that allows for less driver error. The chute will be lined with 4 sets of 3 wheels to push the cube up the inclined plane, which can reach over the switch fence as well as the portal to deliver a cube. See over here we have, an example, if you can see that.
Hold it up.
Oh, yeah, sorry. The cube intake consists of 2 flexible arms equipped with motorized wheels to help the cube start its journey up the chute. What he's also grabbing. Thanks, Julia. Chute dimensions, length 38 inches, and then horizontal length 32.25 inches, inner width 15 inches, height 16 inches. And yeah. Go ahead. Thank you. Manipulator 2, climber. The climber is undecided, however, the options open to us are a pneumatic system which extends to the bar via pistons and lifts the robot up a foot, passing the climbing requirements. And also a folding platform that allows for 2 120-pound robots to climb aboard a robot during the climbing portion of the match. We possess the levitate power-up. You can climb while lifting another robot up 1 foot, which will be transitively supported by the platform. And here's just a few slides of programming. Yeah, just real quick. We decided for a programming language to be Python, and we are working on using vision processing on a Raspberry Pi to help with autonomous mode. And that's all. Thank you.
Questions?
Oh yeah, question.
Before we switch?
Yeah. Cool.
Yeah, I have a question.
Oh, you do? All right, yes.
I had a question.
You had a question.
I had a question. Can you show a little bit more about the way the wheels
Sure, yeah.
plan for the wheels is?
Specifically?
Yeah, shoot.
Yeah.
So people have a better idea.
Yeah. So the wheels, so like I said earlier, there's going to be 4 sets of these wheels, so 4 sets of these hex shafts with 2 wheels. They're all going to be connected via chains on these 3D printed sprockets. And so those will all be driven by 2 mini stems. But basically, they all interlink in order to all suck the cube up and kind of push it out. And the arms work in a similar fashion, where the arms will come down and rotate in order to grab it, and then the chute wheels also spin in the same direction in order to push it out. Now that's also able to be reversible, so that way we can take a cube out or accept it or anything. So is that pretty good?
Yeah.
Yeah. Okay. Any more questions? Yes.
What are you guys using vision processing for?
We're going to be, hopefully we're going to try and use vision processing to determine, like, for the switch with the random LEDs. So with the randomness, we want to be able to use the vision processing to say, okay, we need to go this side of the switch, right side, or left side, and so that way it can automatically move and determine which path to choose. Yes.
How do you imagine your climb integrating? Can you show a little bit about your climb mechanism, how that would work?
Yeah, we're still kind of deciding that. Again, going back to the opposite or the other options we have, if we were going to do the ramps, we would attach here on the sides with what room we have on the drivetrain on the exterior sides, and then if you were going to focus just on our self-climbing, we would probably attach pneumatic systems up here and use the height advantage that we already have with the chute, and then extend off of that, and then retract in order to gain that one further. Any other questions?
Okay, excellent. Let's give him a hand.
Hi, my name is Hi, my name is Hope Kudo. We're the Tiki Techs. Ah. Oh wait, this is.
Hi, I'm Kavika. So, in scoring, in Autonomous, each bot that crosses the auto line scores 5 points for their team. And the switch ownership and scale ownership earns 2 points per second. However, in Teleop, it swaps to 1 second. And then each cube inside the vault scores 5 points for the team. The boost power-up gives 2 points per second to the scale or switch or both. Parked on a platform in order to climb is 5 points, and then each bot who successfully climbs scores 30 points each.
So in terms of game strategy this year, we developed our game plan based on getting points during the autonomous and climb mostly. So during the autonomous, our programmers are working on developing a code that's applicable for every language where each bot on our alliance would be able to cross the autonomous line, not only scoring 5 points for every bot that we get across, but we prioritize scoring in the switch as well, like the Wea team. And by scoring a power cube in the switch during autonomous and getting all 3 bots across the auto line, we are hoping to get a ranking point from that. And ranking points are pretty essential in the game. They help us get a higher rank and get a better alliance. So we are also trying to prioritize the climb. So by doing that, our bot will be having these drop-down wings, and we are hoping to lift 2 bots up with us during the climb, since it is a very small area that we'll be trying to climb up. So every bot that we get in the air during the climb will be 30 points each. In addition, we'll also be getting another ranking point. So we're hoping to score 2 ranking points for every match. And then we're gonna try and optimize the power-up capabilities. Not really the levitate, since we'll be able to use those power cubes in order to score in our switch, but we'll be using the boost and the force power-up in order to gain control of the switch and the scale, and double our points during that time.
So hi, I'm Nicholas White. So our lift that we have is a 3-stage linear slider lift that is based off the one in Robot in 3 Days.
It is using one 775 Pro to Versa Planetary gearbox at the base of this linear slider. It has that rotates a chain which will go up this, and then it will pull up this what's it called? The carriage, and then the carriage will collide with the second stage, and then that will lift it up, and it will lift up to a total of 82 inches.
The carriage we're going to be putting onto our intake. They'll be able to take the cube up to score. We're going to use a small spec there. And then also on the top here, we're going to add 2 hooks that we're going to use for the climb, which we can attach to the pole to climb.
And then for the intake, we have this, which is a wooden model, and up there is some prototypes that we had. It would have arms on the side and then wheels in the middle, so that we would be able to grab the cube in any orientation, and the arms on the outside would collapse, and we would be able to grab it, and then their wheels purpose is that we can also suck it in and also spit it out if we ever need that extra distance.
So those wheels on the intake are actually squishy wheels, and basically what they allow is that when you suck in the cube, they will compress and then give a better grip on the cube so that we can lift it up and down.
And then also for the wood intake, for prototyping purposes, we cut it on that side so we could expand it and compress it to see what distance would be perfect for the cube fitting in.
Okay, so last year for programming, our team used LabVIEW, but our computer vision team used Python, and they weren't able to interact very much with each other. So this year we are using, originally we were going to use Python, but we discovered some issues with library compatibility, so we switched to Java. And for additional practice, our programming team programmed last year's robot in Java and got full functionality with that. This is also our first year using GitHub to manage our projects. We posted all of last year's both robot code and vision code there if you're interested in checking that out. And some of our objectives for this year include automatic shifting between our two-speed transmissions, depending on the load on the robot. And we also want to, like what Hope mentioned earlier, is write basic autonomous code for teams at competition that might not have one, just to cross that line in autonomous and gain a few bonus points. And we're also working on a virtual simulator so we can test all of our code and autonomous code on the robot without having it finished or the field built.
Hi, I'm Brock Taylor, and for electronics, for the drive base, we're using Talon SRX motor controllers, which allows us to use the built-in features of motion profile control, which is much more consistent than normal motor control. And then for the rest of the robot, we're using PWM with Victor SP's motor controllers, because we didn't see the need for Talon SRXs when we can just use other sensors and encoders to get the same similar results.
So, for the frame, most of it was sawed off with a circular saw, with the belly pin being cut first to its size, down to size, to then be cut with the angle grinder to get any indents in the actual belly pan. The belly pan is now that is thicker compared to last year's. We bracketed it down so that we could weld it, and
yeah, so basically we welded the frame together and we were able to get everything square, although that was a little bit of an issue since they were all freestanding before we bracketed it. So yeah, so you might notice that our drive base actually has 3 different wheels on it. We've got blue wheels, we've also got yellow wheels, and those wheels that have wheels on them. So, so in the front, this is a 6-wheel drive. It's a West Coast drive, so that means that only 4 wheels are ever driving at the same time. So the wheels in the front are enabling us to maneuver in an open field, while the yellow wheels in the middle act as paddles, since they have a traction that is like able to easily maneuver on slippery surfaces, while the back wheels have carpeted surfaces are meant to grip onto frictionless areas. So basically, through this process, since it's a West Coast drive, only 4 wheels are ever going at one time, meaning that we actually have a 2-in-1 drive base. So while we are going forward, we're going to be able to have that maneuverability that we desire in like a non-wheel drive base. But if we're getting pushed back, we have the friction to push back on another robot. So in addition to this 2-in-1 drive base, we've also got a shifting transmission. And in its torque speed, we're going around 8.5 feet per second, or feet. Yeah. And then we're going 17 feet in our speed section. So through this, we've actually been practicing on last year's robot on these like Friday night drive sessions, and we've been using the speed moment, the speed part of that to get that experience.
So this is our drop down. These are kind of our buddy bars for the other two robots in our alliance. Basically they drop down like that simply, and we're gonna put ramps on both the front and the side so that they can board the bars either way. And on the right here are some CAD prototypes. They were originally analyzed for their the stress and the weight put on them, as you can see in the corners here. Oh my god, that's not the place. So with just the 1x1, the weight would have obviously been really hard on the joint, so we replaced it with a sheet metal kind of material more, so that it would distribute the weight more evenly. This was put together by one of our alumni students who is now in Stanford, and yeah.
So the reason why we did that demonstration, as you may have noticed, was to prove how strong this material was. So it's capable of lifting lots of heavy robots to maximize that climbability.
So for the end game, we have 30 seconds left in the match to start the climb, and that's when the robots will board our buddy bars and initiate the lift. If all three robots make it up together, that'll give us a whole ranking point. And
all right. Questions?
So be sure to come out to KLKH High School at the cafeteria on President's Day from 10 to 4, where you'll be able to see our robot in action and actually be able to drive it for yourself as well.
So I have a question. Yes. So on the lifting part, you said 30 seconds was how long there was in the very end game when you can lift. How long do you estimate that it'll take you to lift three robots?
The end game is 30 seconds long, and we estimate that our robot will take 4 seconds to lift. Any other questions?
What time is the action? It's 10 to 4, so it's a 6-hour game?
Yeah.
Okay. So we can just come in at any time.
No other questions? All right, well, thank you. Okay, so hopefully some of you guys will stay up here so that if people want to come up and take a look at the robots, that if they can, you can answer specific questions about the robots.